Momentum change and impulse. Suppose that there is an event that changes the object's momentum from p0, which is the initial momentum just before the event, and that's a vector, see it's in bold type, and it changes by delta p, the change in momentum. Finally, it becomes the final momentum, p or pf, either one, and that's just after the event. The vector equation for the change in momentum is delta p is the final momentum minus the initial momentum. We'll start with the momentum change equation, and then Newton's first law states that the velocity and so the momentum of an object won't change unless the object is affected by an external force. We will define impulse, or J, as an average external force acting on the object for a time delta t. J is a vector and is in the same direction as the net external force on the object. The impulse changes the momentum of the object. So here's our definition of impulse, and here's the fact that it changes the momentum of the object. We'll put those two expressions together and we get the impulse momentum equation. Many textbooks and websites use I for impulse. The College Board AP Physics exams uses J, so we'll use J. Now start with the impulse momentum equation, relating the net force on the object with time and momentum. Divide both sides by delta t. This expression shows that a net applied force on an object or a system equals the time rate of change of its momentum. If the net external force on the system is 0, then the time rate of change of momentum is 0 and momentum is conserved. Conservation of momentum applies equally to a system of particles as well as to solid objects. And now for something really cool. We start with the impulse momentum equation, then we substitute in mv for momentum. Since m is a constant, bring it out of the delta sign, so we have m delta v over delta t. And what's delta v over delta t? It's acceleration. Acceleration is a change in velocity. So we have Newton's second law being derived from the impulse momentum equation. And of course, you can also go backwards, start with Newton's second law, and derive the impulse momentum equation. Now let's look at Newton's third law. When two objects interact, the impulse on one object due to the second is equal and opposite to the impulse on the second due to the first object. This is a consequence of Newton's third law, as impulse is a function of force. If there are no external forces on the system of two objects, then an increase in momentum of one object is equal to the decrease in momentum of the other after the collision. By choosing the correct system, the conservation of momentum can be invoked to solve problems, including the velocity of the objects within the system after a collision. Consider two baseballs bouncing off each other. If the system is defined as one of the baseballs, total momentum is not conserved as the baseball's momentum changes. The second ball exerted an external force on the first ball. The momentum is transferred from the system to the environment, the second ball, or from the environment to the system depending on the type of interaction. But if the system is chosen as both baseballs, then total momentum is conserved as there are no external forces. The velocity of each baseball immediately after the collision can be predicted with equations that will be covered in the next topic. There is no specially named unit for impulse. We just use the product of the units of force, newtons, and time, seconds. So we get kilogram meters per second. This is the same unit that we use for momentum, which is a good thing. Let's look at the impulse momentum equation graphically. We have impulse is F delta t, force times the time that it's exerted over. Force is inversely proportional to delta t. So, for example, if we change delta t by just a little amount, we can greatly change the force exerted on an object. For example, let's take this point over here. The time there is a little less than 1 second, and the force is about 130 newtons. If we just change to about 4 seconds, if we extend the duration of the impulse to 4 seconds, you can see how the force drops dramatically. And as you go longer and longer at your time interval, there's less of a change in force because frankly it's getting very tiny. Another way to look at that is we have impulse divided by delta t equals the force applied. So you can see as delta t gets smaller, F gets a lot bigger. Now we're just going to work with the magnitudes of the impulse and momentum going forward, so we're going to leave the vector sign out for now. The bold here is to show that if delta t is small, F is large. If delta t is large, F is small. The inverse relationship of force and time interval leads to many interesting everyday applications of the impulse momentum equation, such as car structural safety design, car airbags, landing on the ground after you parachute safely from an airplane, the martial arts, and both hitting and catching a baseball. We're going to look at two specific cases from the previous list, car airbags and hitting a baseball. The analysis we're going to use is very helpful. You can use it in many other cases in physics when you have an equation with three variables. In this case, the three variables are force, your time interval, and of course, impulse, which again is your change in momentum. So you have the three variables. You have to decide, depending on what case you're analyzing, which value is fixed and then which will be varied, and then that will determine the impact on the third variable. For example, for the car airbags, we'll fix delta P, we'll take different scenarios of the time interval and see what the impact on the force is, and in this case it'll be the force on the people inside the vehicle. For a bat hitting a ball, we will fix the force with which the player hits the ball, we'll vary the time interval, that's how long the ball stays in contact with the bat, and we'll see what that does to the momentum of the ball. In the dynamics unit of this course, it was shown how during an accident, seat belts protect passengers from the effect of Newton's first law, the law of inertia, by stopping the passenger with the car and preventing them from striking the dashboard and the window. Inertia, the law of inertia says you keep moving until there's a force that stops you. That's one of the things it says. So if you are not seat belted in, the car stops because it hits something or you apply the brakes very quickly. And if you are not seat belted in, the frictional force between your body and the seat is not enough to stop you. So you'll go flying forward as the car stops, which is never a good idea. Also, the seat belts provide another benefit explained by the impulse momentum equation, and this benefit is greatly enhanced by the presence of airbags. Can you see what this benefit is? Take a second before you go on to the next slide and see if you can figure it out. The time interval delta t. The seat belt increases the time interval that it takes the passenger to slow down. You don't go flying forward and hit the glass. The seat belt has a little play, so you move a little bit, but then it slows you down when it tightens up. The biggest effect here is the airbag. That increases that time interval. It rapidly expands, providing a cushion that you strike. Then it deflates, and it's slowly compared to how fast the car has stopped, bringing you to a stop. Very analogous to if you fall from a height of 3 feet onto the floor, that hurts. Your time interval of this stop is very, very short. If you fell the same height onto a mattress, the mattress would give, increasing the time of you stopping. There'd be a greater time interval. Earlier we stated that delta P for this example, for the car airbag would be fixed and delta T would be varied. Well, we just talked about why delta T is varied. Why is delta P fixed? Delta P is fixed because as long as the passenger remains in the car, which of course is another wonderful reason to wear your seatbelt, the car and the passenger started with a certain velocity and finished with a final velocity of 0 independent of the seats or the airbags. Whether you had them on or not, the car is going to stop. By rearranging the equation, F is delta P over delta T, where F represents the force delivered to the passenger due to the accident. We have the impulse momentum equation up here, where F delta T is equal to the change in momentum. And we did a little rearranging on the last page, and we had force is delta P over delta T. So delta P is fixed. So we just draw a little horizontal line there showing that it's fixed. Delta T, we've extended the time interval by using the seatbelt and the airbag. So delta T is going to increase. This is a handy little trick to see what happens to the various variables. If you increase the denominator, you decrease the entire number. So the force, and this is the force on the passenger, decreases markedly. That will mean less physical harm to the people inside the car. Another benefit from the airbag is pressure. Pressure is force per unit area. By increasing the area of the body that feels the force, remember the airbag is pretty big, less pressure is delivered to all parts of the body. That will reduce the chance of puncturing the body, which is also a very good thing. This time we're going to take a case where there is a given force, and we're going to vary the time interval to find out what happens to the change in momentum. This is different from the airbag example, where delta P was constant. That was the car slowing down from a certain velocity to a stop. Delta T was varied depending on the airbags and the safety belt, and the impact of the force on the passengers was found. So let's assume a baseball batter swings with a given force that is applied over the time interval of the ball being in contact with the bat. The ball will be approaching the batter with a positive momentum. We could have chosen negative, but in this case we'll choose positive. What is the goal of the batter? The batter wants first of all to hit the ball, and then his next job is to get the largest change in momentum possible for his force, and that force depends on his own strength and timing. The greater the change in momentum, the faster the ball will fly off his bat, which will result in it going further, hopefully to the seats. He's probably not thinking about getting a momentum change, but he does want to hit the ball very far. Now, of course, hitting a baseball is way more complex than the analysis that will follow. If you're interested in more information, please check out the book, The Physics of Baseball, which was written by Robert Adair, a Yale University physicist. Now you can discuss or think about other examples. But again, make sure you decide which object in the collision is more affected by the force or the change in momentum. For example, with the car bags, you're much more worried about the people than the car. And which variables are capable of being varied. In that case, again, it was the time interval of a collision. So again, for the airbag, the car experiences the same impulse as the passenger during an accident. But a car is much less valuable than a human being. So it is more important for the passenger that less force is delivered to his or her body and more force is absorbed by the car. So here are the examples that we didn't talk about here that you can now think about, research, discuss, and that'll be quite interesting. And it going further, hopefully to the seats. He's probably not thinking about getting a momentum change, but he does want to hit the ball very far. Now, of course, hitting a baseball is way more complex than the analysis that will follow. If you're interested in more information, please check out the book, The Physics of Baseball, which was written by Robert Adair, a Yale University physicist. What we have here is a given force by the batter, and the batter wants the largest possible momentum change. So there's the force. That stays the same. So what does the batter want to do? He wants to maximize the time that his bat, which is providing the force, is in contact with the ball. That means he should follow through with his swing. So by increasing the time that the ball is stuck to the bat, he'll increase the momentum. So the batter will be applying a very large impulse because he will have to reverse the ball's large momentum from the positive direction, heading towards the batter, thrown by the pitcher, to the negative direction, which is heading towards the center field bleachers. A constant force of 12 newtons acts for 5 seconds on a 5 kilogram object. What is the magnitude of the impulse delivered to the system? What is the change in the object's momentum? What is the change in the object's velocity? We write our givens, and we're just interested in the magnitude this time. There's no direction. So impulse equals F delta t. Substitute in our givens, and we get the impulse is 60 newton seconds. What is the change in the object's momentum? Well, the change in the object's momentum is just equal to the impulse, so that also is 60 newton seconds. What is the change in the object's velocity? So here's our momentum equation. Change in momentum is equal to m delta v. We want to find delta v, so we divide both sides by the mass, substitute in our givens, and we get 12 meters per second is the change in velocity. A 0.050 kilogram tennis ball moves at a speed of negative 10 meters per second and is struck by a racket, causing it to rebound in the opposite direction at a speed of 16 meters per second. What is the change in momentum of the ball? What is the impulse exerted on the ball? And finally, what is the impulse exerted on the racket? So here's what's going on. Tennis ball comes in here 10 meters per second, leaves at 16 meters per second in the opposite direction. We'll start by finding the change in momentum of the ball, and here's our givens. Why do we have the negative sign there? We're going to say the left direction is negative. So since the tennis ball is going to the left, its velocity is negative 10 meters per second. Its final velocity is in the opposite direction, or the positive direction, so that gets a positive value, 16 meters per second. So once again, here's our change in momentum equation. Substitute in the mass of the tennis ball, and then substitute in the two velocities, the final velocity and the initial. And again, be sure to have this negative sign in front of the 10, and also be sure to have this negative sign. So delta P will then be 1.3 kilogram meters per second. What is the impulse exerted on the ball? Once again, we have the impulse momentum equation. So the impulse that the racket delivers to the ball is the change in momentum of the ball, and we just solve for that. That's 1.3 kilogram meters per second. What is the impulse exerted on the racket? Well, the impulse that the ball exerts on the racket is negative the impulse that the racket exerts on the ball, and that's minus 1.3 kilogram meters per second. The force that the ball exerts on the racket is part of an action-reaction pair with the force that the racket exerts on the ball. So the two impulses are equal in magnitude and opposite in direction. A 0.030 kilogram golf ball is hit off the tee at a speed of 34 meters per second. The golf club was in contact with the ball for 0.0030 seconds. What is the average force on the ball by the golf club? Now we need to find the average force on the ball by the golf club. So we write our givens, and the initial velocity is 0 because the golf ball is not moving in the beginning. So we have impulse is a change in momentum, mvf minus mv0. Substitute in our givens, and here's your initial velocity, and you get an impulse of 1.02 newton seconds. We now use the impulse definition. Impulse is F average times delta t. We want to find F average, so we isolate it by dividing both sides by delta t, substitute in our numbers, and we get 340 newtons.